Generating complex 3D geometry is no longer the hardest part of mechanical design. Today's tools make modeling almost effortless. The real friction in 2026 is ensuring that the geometry you just modeled actually complies with intersecting global regulations and surviving the multidisciplinary reviews required to prove it. For decades, the standard approach was to build parts in CAD and track the regulatory constraints separately in static spreadsheets. Looking at the flaw section, mapping codes with static documents leads to late-stage spatial clashes, when physical rework is most expensive. Modern PLM reconfigures this architecture. By actively tracking spatial constraints, AI-driven PLMs convert a post-design audit into a generative guardrail. This leaves engineering teams with a crucial decision. Do you pay the migration costs to adopt a heavy AI PLM, or do you piece together agile cloud tools and ultra-realistic renderers? Choosing a platform in 2026 requires a specific trade-off between rigid compliance guardrails and rapid iteration speed. Let's evaluate the Enterprise AI PLM tier first. This system serves as a generative guardrail for highly regulated fields. These systems handle specialized requirements by taking nuclear-grade checklists, like the NQA1 mandate shown in this bounding box, and embedding them into CAD metadata. Notice the hold initiated status. The system physically locks design progression until every NQA1 sign-off is digitally verified. Structural integrity codes are directly mapped to specific areas. Here, the red shell inlet nozzle is tethered to ASME standards, and the system logs automatically validate the weld parameters as the engineer works. Once those strict outer limits are set, the AI takes over the internal components. This log shows the system optimizing the TEMA tube count for fluid dynamics, fully constrained by the preset API pressure boundaries. The trade-off is the initial friction. Reaching this level of automation requires an upfront investment in metadata structuring and forces your team to adhere to a rigid workflow. Enterprise PLMs effectively eliminate late-stage physical rework. But if your team operates outside of heavy industrial design, the administrative overhead makes this system expensive overkill. If your priority is moving fast rather than locking down databases, you have to look at agile cloud platforms and desktop motion solvers. Desktop solvers approach complex assemblies by calculating real-time friction and fit tolerances during a virtual collapse, as seen in Step 2. Moving to Step 3, verifying these physical integrations digitally allows teams to resolve standard mechanical constraints without costly downstream physical testing. When you move that core architecture entirely to the cloud, you unlock real-time, multi-user iteration. Distributed teams can conceptualize and edit simultaneously. However, agility has its limits. Looking at this red safety relief valve, you can see a 1AEA protocol log. Tracking safety-critical paths like this across separate, siloed tools often breaks your digital thread. Patching together cloud agility and localized desktop simulation provides iteration speed, but applying specialized standards across a disconnected stack introduces version control vulnerabilities. The final layer to consider is visualization, exporting digital twins into AI-enhanced rendering engines utilizing techniques like 3D Gaussian splatting. These tools are effective for securing client buy-in. This green instrumentation interface and its corresponding IEEE system log shows how visual clarity helps bridge the communication gap across different disciplines. The limitation is that these are strictly downstream applications. They clearly illustrate final compliance, but they do not mathematically enforce foundational limits while the engineer is modeling. This graphic demonstrates where the real work happens. The structural limits of this blue API pressure boundary require continuous automated tracking against flow simulations. That logic has to reside in your primary engineering tool. High-fidelity visualization is an essential tool for communication, but it is a cosmetic output, and it cannot substitute the structural rigor of active constraint modeling. There is no single perfect platform. The right stack is the one that aligns with your team's most expensive point of failure. This regulatory genealogy matrix lays out the reality of modern design. You are constantly balancing overlapping standard codes, primary variables, and validation triggers simultaneously. If failing to balance those standards results in physical rework and manufacturing delays, your primary bottleneck is compliance. In that scenario, the recommendation is the Enterprise AI PLM. In this case, the capital expense is justified. The PLM AI core acts as a central conductor, tying all of these color-coded components into a single verified system before manufacturing begins. Alternatively, if your main bottleneck is slow conceptual iteration and delayed client approvals across a distributed remote team, forcing them into a heavy PLM will stall your workflow. For that scenario, adopt a modular stack. Combine cloud collaboration tools for rapid modeling with ultra-realistic downstream rendering to accelerate sign-offs. Engineering managers should look past the AI marketing buzzwords. Identify the specific friction slowing down your daily workflow and invest strictly in the tools that resolve it.